Hello and welcome to another video of Circuit Digest. In this video, I'll show you how you can build your very own Arduino based adjustable DC load source like this one. So a circuit like this can be very useful when you're testing a new power source like a newly purchased battery or a DC adapter or your very own SMPS circuit. So what you can do with this module is you can load all these power sources in a sequential manner, that is you can control the output current and see how they perform. To give you a quick demonstration, let me connect this famous 9-volt battery, which is a really dodgy one, to a module and show you how it works. As you can see, our module has two DC adapter plugs. One is used to power our module and the other is used to connect the power source which has to be tested. So I'm using a 12-volt adapter to just power our module. You could use any power source. I'm just using it to power our module, and as you can see, it says circuit digest with some logo information, and then we have three parameters over here. One is the set value, other is the current, and other is the voltage. So the set value is used to set how much current should be drained from the source, here the 9-volt battery, and the I and V shows the current value of voltage and current. So you can see two push buttons over here. One is to decrease and another is to increase the set value. So let me go ahead and connect the 9-volt battery. As soon as I connect it, you can see that a module says that the battery is currently of 8.5 volts and we haven't set any current, so the current is 0 amps. Let me go ahead and increase it to 100 milliamps. As soon as I increase it to 100 milliamps, the module starts to drain 100 milliamps from the battery, and you can see the voltage has already dropped to 6.68 volts. Let me increase it to 200 milliamps and the voltage is already lower than 5 volts, so which means that the battery is not a very good one and the power source is not very reliable if you're consuming more than 200 milliamps. So in this video, I'll teach you how the entire circuit works and how to build one on your own. So let's get started. Let's begin by taking a closer look at our module over here. As you would have already noticed, we have an Arduino Nano which acts as the brain of the entire module. So whenever you connect a DC load to this DC barrel jack, the circuit gets closed through this shunt resistor and the MOSFET. The responsibility of the Arduino is to switch the MOSFET in such a way that the current drained from the source is equal to the current that we have set previously using these push buttons. So this can be done using these two ICs. The first one is a MCP4921 digital to analog controller IC from Microchip, and the second one is the most famous LM358 op-amp IC. Talking about PCB's fabrication, we should definitely mention All PCB, who is the sponsor of this video. All PCB is known for their ultra-fast PCB services. They promise 24 hours of lead time with 2 to 5 days of delivery time. They deliver high-quality PCBs and also promise 24/7 services. If you order now, you can also get 5 PCBs for just $2. To understand how exactly it is done, let's take a look at the circuit diagram. As you can see, we have the Arduino Nano over here, which is connected to the LCD, and we have the other two ICs which I told you, the MCP4921 and the op-amp over here. So let's begin from this DC barrel jack section. As I told you earlier, the DC load which is connected to this particular jack will be connected to a MOSFET and a shunt resistor before it reaches the ground. Now, as you can see, we also have two other resistors over here, R8 and R9, which forms a potential divider. Basically what happens is this potential divider will map down the voltage that is connected to this particular jack between 0 to 5 volt. Say for example, if you connect a 24 volt power source over here, it will convert it into 5 volt so that your Arduino can easily read it. So if you can see, this potential divider maps down 0 to 24 volts to 0 to 5 volts, and it uses a voltage sense label which is connected to the A1 pin of our Arduino. Now to measure the current, we are going to use this shunt resistor. As you can see, the value of the shunt resistor is 0.1 ohms and 5 watts. This means that when 1 amps of current is being drained from the load, the voltage drop across this shunt resistor will be 0.1 volt, which is a very small value, and that is why we are going to use an op-amp to amplify it. So let's forget about this one over here. Let's take a look at only this op-amp. As you can see, the op-amp directly reads the voltage drop across this shunt resistor and increases it with a gain value of 6. The resistors R5 and R6, which is of 2K and 6K, is used to set the gain value of op-amp. In this case, it is 6. So what happens is this 0.1 volt drop across the shunt resistor will be increased to 0.6 volt because of this op-amp. Now again, it has a label called current sense, which is connected to our Arduino over here to the analog pin A0. So with this, the Arduino will be able to read the current as well as the voltage of the power source that's connected to this DC barrel jack. Now all it has to do is to switch this MOSFET in such a way that the current that is being read from this pin is equal to the current that we have set already using the push button. To understand how the current regulation part works, let's take a look at this op-amp. So let me just cover this op-amp, and if we take a closer look at this op-amp, you can see that the pin number 2 is actually connected to measure the voltage drop across the shunt resistor again, and pin number 3 is connected to our DAC, which I will get back to it, and the output pin is directly connected to the MOSFET, so the op-amp can either turn on or off the MOSFET directly. So let's go back to our example where there is 1 amps of current flowing through the circuit, and in that case we'll have a voltage drop of 0.1 volt across the shunt resistor. In this case, the op-amp will read this voltage drop, and hence the voltage here will also be 0.1 volt, and based on the voltage given to pin number 3, the op-amp will either turn on or off the MOSFET. So let's say, for example, if we give 0.1 volt to this pin, then our MOSFET will be turned on as far as the voltage across this shunt resistor is 0.1 volt. If the voltage increases, the MOSFET will be turned off. This will be kept on repeated, like if the voltage exceeds 0.1, the MOSFET will turn off, and hence the current will go down, and when the current goes down, the op-amp will realize that the voltage has gone below 0.1 volt, and it will turn on the MOSFET again, and the current will rise back to 1 amps, and the voltage drop will again be 0.1 volt. So this way, whatever voltage we are giving to this pin number 3, the op-amp will make sure that the voltage drop across the shunt resistor will be equal to the voltage given to pin number 3. So if we want to increase the current, we just have to change this voltage to 0.2 volt, and the op-amp will keep the MOSFET turned on as far as the current flowing through this circuit creates a voltage drop across this shunt resistor, which is equal to 0.2 volts, which will also make pin number 2 0.2 volts. So the op-amp will now keep this MOSFET turned on as far as the voltage is 0.2 volts, and it will turn it off when the voltage exceeds 0.2 volts. So this way, whatever voltage is given to pin number 3, based on that voltage, the op-amp will control the current flowing through the circuit. So this is what is called a voltage controlled current source. So now all we have to do is provide a variable voltage to pin number 3, and to do that we have a DAC, which is the MCP4921, this IC. So this IC is interfaced with Arduino through SPI communication. So from the Arduino we can tell, hey MSP, just set the voltage to 0.1 volt, and your Arduino will talk to your MSP with SPI communication, and your MSP will provide an output voltage which is exactly equal to 0.1 volts. So based on the voltage and the current value that we have set here, your Arduino will ask your MSP to set the analog voltage over here, and as I told you, based on this analog voltage, the current through the MOSFET can be controlled. So this is how the entire circuit diagram works. Hope you understood it. So once you're comfortable with the circuit diagram, you can modify it according to our needs. For example, here I have used a 5 watts resistor, which allows me to control current up to 5 amps, and the potential divider allows me to control load up to 24 volts. So once you have understood how the whole circuit works, you can make few changes if required, like changing the output voltage and the current rating of the circuit, and then proceed with PCB design. I have used Eagle to design my PCB, and the final file looks something like this. You can use any software, but once the design is complete, you can generate a Gerber file like this one. Once your Gerber file is ready, we can proceed with PCB fabrication. To get your PCBs from All PCB, you just have to get into their website, and over here you have to enter the dimension of your PCB. Like mine is, let's assume 100 cross 80 mm, and select the number of PCBs required and then click on quote now. This will take you to another page where you can select few other parameters like the number of layers, and if you come down you can even select the color of your PCB, that is the solder mask color, and few other parameters if you like to explore. On the right hand side we have some interesting parameters, which is like your shipping method and the lead time. For example, if you're selecting DHL, the shipping will be for 3 to 7 days, and you can even change it to Hong Kong Post if you want a cheaper shipping. But let's select DHL and click on add to cart to proceed with our checkout. Now just click checkout now, and this will take you to another page which gives you option to upload the Gerber file. To upload your Gerber file, just click on upload Gerber, and we already have our Gerber file ready. Just click on it, and once the upload is complete, go ahead and click on buy. On the next page you have an option to add a new address, and down here you can check the total price that you have to pay for your PCB. There are two payment methods, one is through PayPal, another is through bank transfer. Select your mode of payment and then click on submit. This will take you to another page where you have to make the payment. Once the payment is made, sit back and relax, and within few days your PCB will arrive at your doorstep. After few days, I received a package from my courier guy, and as you can see for yourself, it was from All PCB. The packaging was very neatly done, and on unboxing, I found our new PCBs neatly wrapped under a bubble sheet. As you can see for yourself, there was no damaging made during the shipping process and everything looks intact. So let me cut it open and bring our new PCBs outside. As you can see for yourself, the quality of the PCB was very good, so I immediately proceeded with soldering all the components and uploaded the code to our Arduino board. The Arduino code for our project is pretty simple. The complete code along with its explanation can be found at the link given in the description of this video. There are three important functions, one of which is the convert_DAC, which is used to communicate with the MCP DAC IC. So this function passes a value called value, and it was used to control the output voltage from the IC. Other than that, we have the read current and read voltage function, which is used to read the voltage and current of the DC load. Inside the loop, we have two important functions which reads the status of the push buttons, that is used to increase or decrease the set current value. Based on the status of the push button, we generate a value on the variable called number and pass it to our DAC using the convert_DAC function. Apart from that, we have few other basic LCD functions which is used to display the set current, the actual current and the actual voltage on our LCD. So once the code is ready, you can upload it to your Arduino Nano and be ready to test your project. For testing our setup, I have connected a 7.4 volt lithium battery to our DC jack over here, and I have powered it using the 12 volt adapter as usual. Now as you can see, the set value is currently 0 milliamps and the battery voltage is at 7.5 volts and the current is also 0 since the set value is 0. I have also connected my clamp meter to compare the reading that's shown on the LCD display with the actual value that's being measured by the clamp meter. So now let me go ahead and increase the current. As you can see, I have increased the set value to 100 milliamps and the current draw is now 100 milliamps, and the voltage has dropped from 7.5 volts to 7.3 volts, and the multimeter here is also showing around 0.14. So there is some error and I was not able to calibrate it very perfectly, but this is by far the most accurate values that I could get. So if I increase it to 200 milliamps, you can see the multimeter actually reads 220 milliamps, but the voltage has dropped to 6.8 volts already just for consuming 200 milliamps. Let me go ahead and increase it to 300, and you can see the multimeter also shows 300 milliamps exactly. So this is the sweet spot of the calibration, and the voltage has dropped to 6.8 volts. Let me go ahead and increase the load further. At 400 milliamps, the multimeter shows 400 milliamps and the voltage has dropped to 6.3 volts. Let me go ahead and increase it further at 500 milliamps, and the voltage is already 6.2. Let me just go up to 700 milliamps, and you can see the voltage is almost 6 volt, and I think this is the maximum current that I could load this battery for. So this way you can also leave the battery in such a state and see how far your battery is able to discharge this particular current. Here I am not risking loading the battery because there is a safety circuit inside this battery, but if you're using a battery that doesn't have a safety circuit, be careful that you're not overloading the battery. So let me just increase the current to 800 milliamps. As you can see, the multimeter is still reading 740 milliamps. When you're doing some heavy loading, just make sure you're adding a heat sink to your MOSFET, because your MOSFET would get really hot. And let's just go up to 1 amps. So this is 1 amps. The multimeter also reads 900 milliamps, but even the multimeter is not up to the mark. So let's just assume that it's 1 amps, and the voltage has dropped to 5.3 volts. So I think this is the maximum I could go with this battery, but let me just go up to 1.2. And as you can see, at 1.2 the multimeter also reads 1.12. So let's decrease and go back all the way down to 300 milliamps. Okay, so this way you can set the current and then monitor how far your battery is able to supply that continuous current. It doesn't need to be a battery. You can also use an SMPS circuit and see at what loading current your SMPS shuts down. So there are so many advantages for using this adjustable DC load. Hope you like the project and enjoy this video. Thank you for watching. Bye bye.